Well, hello, ladies and gentlemen. We're going to continue on with our investigation of the second law of thermodynamics. Last time we set the ground rules, which is a set of vocabulary about spontaneous processes, natural processes, reservoirs, cyclic devices, coefficients of performance, efficiency. So we set the ground level for our discussion of the second law of thermodynamics. Now, what's to come is going to be a little bit strange. I think I alluded to it before. You're going to see a lot of pictures and a lot of sketches. There aren't going to be a lot of numbers for the next week or so. Well, for the next day or so. The second law of thermodynamics is pictorial in nature, and later on we will be adapting it to numbers. So for those of you that like numbers and calculations and equations, just be patient. Within a day or two, we're going to be getting back to equations and numbers. But in the meantime, we're going to be working with figures and sketches, pictures, if you like, about how the universe works, and in particular, pictures describing the second law of thermodynamics. So that brings us to our topics today. We're going to go over two statements or two versions, pictorial versions of the second law of thermodynamics, the Kelvin-Planck and the Clausius statement of the second law of thermodynamics. Then we're going to be moving on to the limits of efficiency. What's the efficiency of the most efficient heat engine we can build? What's the coefficient of performance for the most efficient refrigerator we can build? So we're going to talk about the limits of efficiency in terms of maximum numerical values for efficiency. And then we're going to actually get back into the math a little bit and describe how we're going to calculate the maximum efficiency and coefficient of performance for a heat engine or a refrigerator. Okay? So those are the topics for today. So let's get started here. The second law of thermodynamics. Second law of thermodynamics. Well, there are two versions of this law, and they are both pictures. Let's say we have a reservoir. Remember what a reservoir is? A reservoir is a very large system such that no matter what the heat interaction is, temperature remains essentially constant. So I have some sort of a reservoir. Kind of a reservoir here. And this reservoir feeds a certain amount of heat, QH, into a cyclic device. And this device is a heat engine. Remember, a heat engine produces work. It takes heat and produces work. So this heat engine supposedly produces a certain amount of work over the cycle. Okay? What the Kelvin-Planck statement of the second law says, this situation is not possible. In other words, work over the cycle cannot be greater than zero. So write work cycle greater than zero and put a big cross over the top, a big X. A device working in a cycle cannot extract heat from a reservoir and produce the equivalent amount of work. So that is the Kelvin-Planck statement of the second law of thermodynamics. This device cannot produce work interacting with a single reservoir. Now, one thing I will say, work could be done on the device, and we could reject heat to the reservoir. That's possible. Instead of the device producing work, we could do work on the device, thereby rejecting heat to the reservoir. That is possible. But it is not possible for any heat engine to produce a net amount of work over the cycle interacting with a single reservoir. Okay, so that's the Kelvin-Planck statement of the second law. And it's a picture. It's a picture. There's another statement of the second law. We have two reservoirs, a high and a low temp reservoir, TH and TL, TH and TL. We attach a device, a refrigerator, and a heat pump, or some device working in a cycle. So a refrigerator or a heat pump. Okay? Now, refrigerator or heat pump normally requires a work input to lift heat. Q low from the low temperature reservoir and shove it up to the high temperature reservoir. Usually requires an input of work. This device here, this magical device, requires no work to lift heat from a low temperature reservoir and pass it up to the high temperature reservoir. This is not possible. Okay? So, two versions of the second law. One is the Clausius statement. Clausius statement of the second law. A workless device operating over a cycle can lift heat from a low temperature and force it into a high temperature reservoir. That is not possible. And then we also have the Kelvin-Planck statement. Kelvin-Planck statement, which says that it is not possible to take heat from some reservoir at temperature TH and rejects a certain amount of heat QH. It is not possible to take QH from a single reservoir and produce a certain amount of work W over the cycle. Not possible to produce work while the heat engine interacts with a single reservoir. So this is not possible. Not possible. Two pictures, not equations, pictures that describe the second law of thermodynamics. One is more, I think, suited for engineers, Kelvin-Planck statement, which says that any heat engine that produces work cannot interact with a single reservoir over the cycle. And then this Clausius statement, I think, is more applicable to physicists. Heat naturally flows from hot to cold, not the other way around. We cannot develop or build a workless device which magically extracts heat from a cold place and shoves it up into a hot place. Okay? So two versions of the second law, and they are both pictures. By the way, they are both equivalent to each other. Why might they be equivalent? Well, let's take a moment here to show that they're equivalent. Let's take a moment to show that they're equivalent. Let's say Let's say I have a high temperature and a low temperature reservoir. High temperature and a low temperature reservoir. And I have a refrigeration device. And this thing works in a cycle, so it's a refrigeration device. So I have a QH refrigerator and Q low refrigerator. The heat transfer from the low temperature reservoir by the refrigerator, the heat transfer to the high temperature reservoir by the refrigerator. And real refrigerators that we know we can build require a work input, work cycle for the refrigerator, okay? Now, let's say we have a Kelvin-Planck violator. What do I mean by a Kelvin-Planck violator? I mean a heat engine that operates by interacting with a single reservoir only. So I'm going to put in a Kelvin-Planck violator. So I'm going to write here, KP violator. And I'm going to use this Kelvin-Planck violator to drive the refrigerator. Okay? Now, if I put a control volume around the Kelvin-Planck violator and the refrigerator, what do I get? I get the following equivalent system or device. The following equivalent device. T high, T low, and I got my device. Okay? Same control volume that contains the refrigerator and the Kelvin-Planck violator. So it's the refrigerator plus KP violator device. It is extracting a certain amount of heat, QL ref, and forcing that heat into the high temperature reservoir. QH net heat transfer to the high temperature reservoir equal QL ref. Okay, that's the equivalent device, taking a certain amount of heat from the low temperature reservoir, shoving it into the high temperature reservoir. So if you pair any device with a Kelvin-Planck violator, you get a violation of the Clausius statement of the second law. This device transfers heat from a low temperature reservoir and magically forces that heat into the high temperature reservoir. So this thing here, Clausius violator. Not possible. Oh, running out of space here. Not possible. Okay, so the Kelvin-Planck and the Clausius statements are equivalent because I can connect a Kelvin-Planck violator to any refrigerator or heat pump, and I get a violation of the Clausius statement of the second law. So either one of them can be used. They're both equivalent. You should memorize both statements of the second law. You need to commit to memory both the Clausius statement and the Kelvin-Planck statement of the second law of thermodynamics, understanding that they are equivalent. They are equivalent.